I don't know how we're gonna introduce this. Do you want us to read the title? I can hey. Is it recording?
Do a song and dance for him. He would like it if it were amusing.
And I'm in my Captain America outfit.
And now, Science on the Side with Gabby and Brittany.
Hi, I'm Gabby.
Hi, I'm Brittany.
And today we're talking about nuclear chemistry, consumer products. Nuclear chemistry is the subfield of chemistry dealing with radioactivity, nuclear processes, such as nuclear transmutation and nuclear properties.
Nuclear chemistry up here, which is actually part of the giant spiderweb of different branches of chemistry. The history of nuclear energy started in 1895 Germany, where the physicist Wilhelm Röntgen was experimenting with cathode rays in a glass tube that he had sucked the air out of.
At one point, he had the device covered, but noticed that the photographic plates off to the side were lighting up when the device was energized. He realized that he was looking at a new kind of ray, and called it what any reasonable physicist would call it, any unknown, an X-ray.
He systematically studied these rays and took the first X-ray photo of his wife's hand, which you see here, 2 weeks later, thereby becoming the father of modern medical diagnosis.
Other influential people involved in the development of nuclear chemistry include Ernest Rutherford, who was the first to distinguish alpha and beta particles, discover half-life, and theorize a neutron.
So here we have a graph of how half-lives work. With each half-life, the activity or the amount of the radioactive isotope actually decreases by half, which is actually why they call it a half-life. In 1896, Henry Becquerel expanded the field of nuclear chemistry when he discovered that uranium emitted radiation. Soon after Becquerel's discovery, Marie Curie began studying radioactivity and completed much of the pioneering work on nuclear changes.
Curie found that radiation was proportional to the amount of radioactive element present, and she proposed that radiation was a property of atoms as opposed to a chemical property of a compound. Fun fact, Marie Curie's notebooks are so radioactive that they must be kept in a lead box, as well as the doorknob that she used.
Now that we know about nuclear chemistry, what exactly does radioactive mean? An unstable nucleus is considered radioactive, which means it spontaneously emits small particles of energy called radiation to become more stable. So here we have a radioactive ion, and energy is being released, radiation, and this could be an alpha, beta, or gamma particle.
A stable atom is an atom that has enough binding energy to hold a nucleus together permanently. Many nuclei in nature are very stable, which means it has emitted enough radiation to bring the ratio of its protons and neutrons into balance, therefore making it non-radioactive.
On the other hand, in unstable nuclei, the strong nuclear forces do not generate enough binding energy to hold the nucleus together permanently, making it radioactive, which is why you get the particles off of radioactive isotopes and other radioactive material.
So like Brittany said earlier, radiation can take the form of alpha particles, beta particles, positrons, or gamma rays. And this chart shows differences between all of those, including...
This chart shows how varying radioactive particles are able to penetrate through an assortment of different densities, which can also allude to the danger level of each particle.
Nuclear fission is the splitting of a large atom into two or more smaller ones.
While nuclear fusion is the fusing of two or more lighter atoms into a larger.
These two processes are very different. Fission does not occur naturally, but is a product of most laboratories, while fusion occurs naturally in stars such as the sun.
Fusion generates very few radioactive particles, unlike fission, that produces many highly radioactive particles, such as gamma rays. Gamma rays are very highly active
Even
particles.
through these differences, what fission and fusion have in common are generating energy, releasing neutrons, and creating bombs.
Now that we know more about nuclear chemistry, we can see how it is translated into everyday items. Many consumer products, from smoke detectors to photocopiers and watches to cosmetics, use small amounts of radiation. But how safe is all of this?
So, ionization chamber smoke detectors contain a small amount of americium-241, a radioactive material. Smoke particles disrupt the low steady electrical current produced by the radioactive particles and trigger the detector's alarm. Because of the long half-life of americium-241, the amount of radioactive material in the smoke detector will be about the same as when it was purchased. They react quickly to fires, and it gives off very little radiation.
Food irradiation is the application of radiation to food to improve the safety and extend the shelf life by reducing or eliminating microorganisms and insects. It makes the food safer for the consumer, and the most commonly used radiation are cobalt-60 and cesium-137. Food irradiation has been approved by the CDC and the USA. If you see this symbol, it means the food you are eating has been irradiated.
Using radioactive substances in our consumer products help lower pollution, lower operating costs, and increase reliability.
On the other hand, nuclear accidents, high costs, danger to humans, and the possible environmental hazard keep people questioning if radioactive is the answer.
We feel as though the positive outcomes of nuclear chemistry being used in consumer products outweigh the negatives.
The history of nuclear energy started with physicist I don't know how to say his name.
Rontgen.
Rontgen. Okay, I'm gonna start that over.
At one point, he had the device covered, but noticed that the photographic plates of this off to the
Same? Yeah.
Curry found that radiation was proportional.
On the other hand, an unstable No. Okay, I didn't know scrolling would do that.
In creating bombs. They react quickly to fires, and it gives off very little radiation.
So little.
So